Martin-Left theory, to be precise. And I told you that we're going to leave the best for last, and today is all about propositional equality. And because I think it's very important and I want to make sure I go very slow, I will be writing on the whiteboard. There is hopefully on the website a link to the document I will tell you all about, because this time I'm actually, not following the way it's presented in the textbook, because in the textbook the propositional equality is defined not two-sided but one-sided, and I want to do the two-sided one because I feel like it's a little bit more standard the way it works, and I just prefer it, and hopefully you'll see why. Before I do that, I saw a really good comment on Slack about how the textbook and consequently how I presented the induction principle for natural numbers. And the complaint was that, well, why are we using pi types to define rules for natural numbers? It's not very modular. And I think even Vita made the point that it's not okay. It's okay to have pi types, you might as well use them, but it's not necessary to do it, right? So there is an alternative way to write the induction principle for natural numbers. And maybe I'll just give it to you. It's also in Slack. Somebody posted it. I really liked it. So if I have a natural number in the context, and then I have a dependent family, and then I can give myself P0, P of 0, and then I can give myself the successor, but without the pi type. So I can write like gamma, and then I need little n, and then I need a proof. If P of n holds, then I can give myself PS as a type P of successor of n. And of course this PS depends on n and all other stuff in gamma. So actually by moving stuff to the context, I am avoiding using pi types for specification of this rule. And to the conclusion, I again move a natural number in the context, and then I give myself the induction on n, and it depends on big P, on little p0, on little ps, and on n, and it will give me big P of little n. Alright? So I can write the induction principle for natural numbers without referring to pi types at all. And personally, I prefer it this way because if we're going to think about how theoretically we pose natural numbers, you can have natural numbers without having functions, right? You can have no dependent functions in your type tree, but you have the inductive definition of natural numbers. And if you use a rule in this form, you can just express it. That was a question there.
Yeah, it feels like this is just deferring the use of functions in a way, because we want to view this induction thing as like a recursive function kind of thing in the end if you want to use it, right?
Yes, so you can just use it by substituting stuff.
Okay.
So because you have here n in the context, what I can do is use a substitution for whatever term I want to use it with, and then I will get the induction term of the proof of that. So I agree it's kind of, morally we're really, doing function application. But technically we don't have to. Like substitution and the rule in this form is kind of enough. So it's just another, morally it's the same. I'm just saying, if we're very nitpicky, we didn't need to use function types, and this is really important. Okay. And now the so promised propositional equality. So why is propositional equality so important? It's because actually equality is super important. Like, even if you're not doing type theory, like if you're doing like regular math, whatever that is, like you want to say that things are equal, and then you want to prove that certain things are equal, right? So if you define addition, for example, then you want to prove that, I don't know, 2 plus 2 equals 4, or that, you know, we defined addition with the induction on the second argument. So we know that judgmentally, we know that 1 plus 0 is equal to 1, just because if the second argument is 0, we have a judgmental equality that defines it to be 1. However, 0 plus 1 being equal to 1 is also something we believe is true, especially if we believe that, you know, addition is commutative, which it is. But how do we express proving it? It's not judgmentally true, right? It won't reduce judgmentally to 1, but we have to be able to express that, well, actually, it is okay. And the way we do it is by introducing propositional equality, right? So propositional equality and we sometimes also call it the identity type. So that is a type. So the idea is that if I have 2 elements, A of type A and B of type A, then the equality between A and B at type A, this is also a type, right? Because we want to prove equalities, that means, you know, this is the statement that we're proving, so equality is a type. And then elements of such types, right, we consider of identifications between A and B, right? The way A and B can be equal. This is sort of the idea. All right, and then if we want to formally define it, we have 4 or 5 categories of rules. And because we've done this so many times yesterday, what is the first one that I'm going to do? What's the name of the first rule? How do I introduce a type? Formation rule. Good, yeah. There are introduction and formation. Information is to form a type, right? So the formation rule goes exactly the way I described it above. So in context gamma, I have little a of type big A, and in context gamma, I have little b of type big A, and then in context gamma, A equals B at type A is a type. Okay, this is how we introduce a well-formed equality type, and you see that A and B indeed have to be of type A, and A will actually have to be a well-formed type to derive this judgment anyway. Okay? So yesterday I was also hinted by some very clever students that it's really useful if we have an example on standby every time we're doing these things. So I think purple is the only color I can have different from black that might be visible. Okay, so how would be a concrete thing? So I know that 0 is a natural number, and I know that add n of 0, 0 is a natural number, which it is. Okay. Then I know that I can form a type with 0 equals add n of 0, 0. And this is a type. Okay? I'm just forming a type. I don't have an element of it yet, right? So next up, we're gonna see how we can form elements of these types. So the introduction rule, yes, question, yeah?
Is 0 equals 1 a type?
Yes. Might be the end type. the introduction rule is just 1, right? And basically, if I have the same term twice, then I have an element called raffle of that element, and it's of the equality type. Okay? So here, I give myself little a of type big A. I can form the type A equals little a at type big A, and I'm claiming that there is an element called raffle A that is an element of this type. Okay? So basically, reflexivity is built in to this type. Okay? So concrete one, 0 is a natural number, and then I can say that raffle 0 is of type 0 equals 0 as natural numbers. Right? And very soon I will start dropping the indices at the type, because I would say if it's clear from the context and if it's clear by sight which type it is, I will just not write it on the equality anymore. And usually when you write Cox code or Anja code or whatever, you don't want to carry the index always. But formally, we should know that the index is also part of the syntax and it's also important. Okay, and then comes the most important one, the elimination rule. And we call the elimination rule for positional equality the J rule. Right? And this one basically says that, so how do elimination rules look like, right? They tell you basically how to form functions out of the type, right? And in order to form functions out of the equality type, the propositional equality type, the J rule says it's enough to define it on reflexivity, and then everything else is, kind of given by the J. Okay, so formally, this says that if I have something that depends on equality, so I'm giving myself an X in type A, a Y in type A, and I'm giving myself a little p of type X equals Y at A, okay? And then I'm giving myself a dependent type family over these things. So I have big P that depends on X, Y, and little p, and it's a type. Then I can form functions of this. And it basically says I have something called J, so J is my new symbol, that has type, give me a diagonal. So diagonal means for every little x in A, if I have p of x, x, and raffle at x, if I have this thing, then I have a function out of all of them. So it's little a, little b in A, any proof little p, okay, I'll call it q, just to be consistent. Little q of type A equals b at A, and then I have an element of p, a, b, q. Okay. What J is saying is that if I give myself the diagonal whenever x and y are equal, and we know how the function behaves on raffle, then I know how the function behaves in total. Okay. What would be, okay, concrete terms so that you have some sort of idea. So of course it's going to be the natural numbers. So give ourselves a natural number x. Is this big enough? Do we have a zoom thing that is?
Yeah.
Yeah, okay, good. If I'm giving myself x, a natural number, y, a natural number, p, that says x and y are equal, then my type family, right, the equality that I will want to prove is that x equals add at natural numbers 0 y. Okay? So this is my dependent type family p, and it's going to be a function out of the equality type, because this here in the context is an equality type. So this is basically saying if I know x and y are equal, then x is equal y plus 0. Okay? X and y are equal, and then 0 plus y is y, so x and y are equal. This is, you know, what is first grade math. Okay? This is what I want. And the J rule for that one would be, I have J that says I have a function, x is a natural number, and then if I'm giving myself the diagonal, where x equals add 0x, okay, then I can give myself the function for x and y that are not syntactically, now physically, you know, equal. So x is a natural number, and y is a natural number, and q is an identification of x and y. Then I can say x equals add 0y. Okay? So this is the idea. Of course, if you want to say something interesting here, it's often, not always, but often also an equality type or some derivation after the equality type. Huh? The last rule, well, I'm lying to you again. We're still missing one category of rules, which is computation rule. Yes, another question.
Why do we need two x's? Like, we have p, x, x, right?
Yeah, because p depends on x, y, and p, and we're saying that this y here is actually an x. That's why it's the diagonal. Yes.
Yes.
Yes. Question?
On the example, the top part of the rule, we're not depending on p, but it says that what would
Yes.
p look like?
No. Don't ask me that. I will give you two more examples of this rule, but I don't think any of them really, you know, depend on, like P is usually REFL or some J of something, and it's really hard to have a good example that is, you know, understandable. Like how can you depend on REFL, which REFL or which J or something it is. So, you know, in principle it could. I'm not saying that it can, but I personally at this stage don't know how to give you an example that is not bullshit. So, good question. I don't know how to answer that at this stage. Yeah.
Sorry, just to make sure that I understand this at like the highest possible level of abstraction, which is probably the wrong way to phrase this, right? And it's the idea that if I know a property, or if I know about a property P that mentions X, and I know that X is equal to Y, then P is true of Y as well. Is that what we're trying to capture with this rule?
This is called transport. I will do this in like, I don't know, 30 minutes. Yes. More question? No? Okay. Computation rule. computation rule basically says that I specified here, if you want to specify, so if I want to have a function, it's enough if I specify it on the diagonal, and then I have it for all. Now the computation rule will say, well, if I use the J rule, then the thing that I get here better be equal to the diagonal where x and y are true. Right? So it's the natural one. The thing that I gave it, it should still be true. Okay, so the long way of saying this is, so I'll write the conclusion first, so that you see where I'm going with it. So if I have a J that takes something of this form, I call it D for a diagonal, and then I'm taking the same element here for A and B. So I'll say little a, and then of course the raffle of little a. Then this has to be judgmentally equal to the diagonal at A. And this is at type P of A, raffle A. Okay. Now what are my premises? Well, I have to specify all of the things that, make it true. So I need to have P of x, y, little p, and the premises like that. The context here is the same as the context up there, and I'm lazy and I won't write it. And then the diagonal is of the correct type. So it just has this type here, little x in A, P of x, x. And then I need to have little a of that big A for this application, so to say, of J to make sense. Okay, and this is the computation rule for the set. And you can just insert yourself the x and add 0 y everywhere here, and you will see that if I specify something on the diagonal here, right, then we should get the same thing. Okay, so my question now would be for you, okay, how would I prove this? Okay, so if I want to have a term, if I want to have a function like this, right, I want to create a term of type for every x, for every y, for every q, that is an equality between x and y, propositional equality, that x equals propositionally and 0 y. Okay? So we know that if we want to have something here, it's going to be j, right? Because I can just use that rule that I wrote here. Okay? So I know that it has to be j, and it has to be applied to a diagonal. So I need to provide something here that is of type for all x equals and 0x. Okay? Now, obviously, I can have an x here, and then I need to provide a proof that x equals the addition of 0 and x. What about now?
Do you need a definition of addition or something?
Oh, we defined it yesterday.
No, I meant like as a premise.
Yes, it's a premise.
Maybe consider x to revel x.
So we need to do something with this addition, right? well, I haven't proved it yesterday, right? Maybe, okay. Let me make this simpler. I will cheat, and I'll swap the arguments. Okay? I get to do that because it's a whiteboard and I can just erase it. So now, I want to add x0. What we want to do, yeah, sorry, go ahead. Yes, so we want to say this guy here is judgmentally equal to x because we defined it this way yesterday, right? And what we really want to say is, well, this is just x equals x, so this would just be reference x. Okay? We can do that. Okay? And we can do that because judgmental equality interacts with propositional equality in a special way, right? And it's basically, you can just compute the left-hand side and the right-hand side according to judgmental equality, and it just holds. Okay? Yes?
Do we actually need J for this particular example?
Yes. It is J applied to this diagonal.
Can we not just take Q directly? And
Yes, we can just take Q directly. Yes. So another correct solution is to just say it's lambda x, lambda y, lambda q, q. We didn't even need to use the induction principle on the facts because I swapped the argument. Okay. Still, I wanna convince you that this here holds, and I will. But there is a rule here missing. Okay? Which rule here is missing? So we have the formation rule, introduction rule, elimination rule, computation rule, and congruence rules. Yes. Okay. Okay, this pen is dying because I took the wrong one. Congruence rules. Okay, congruence rule is this one. Will say that if I have A is equal to A prime, judgmentally, at type big A, and if B is judgmentally equal to B prime at type A, then my pens are dying. Let's get the next one. Then A equals B propositionally at A, our parenthesis here, is judgmentally equal to A prime equals propositionally B prime at type A. Okay? This is the congruence rule. Now, what I want to derive for you is the fact that if I have judgmental equality, I can just kind of use it, right? So I can say that if A is judgmentally equal to A prime, at type A in some context gamma, and then I don't have space, so I will erase this thing, but you have it in your notes, so it's fine. And then if I have that A is propositionally equal to B in context gamma, then what I can do is say in context gamma, I can just rewrite this A and say A prime is propositionally equal to B. Right? And how do I derive this? Well, I have this, and I have this, and I can, well, I want to use the congruence rule, basically, right? Because I have this here in the congruence rule. So what I want to say is that if I do the, I should say something else, actually. I should have a proof. Okay, because this, what I was telling you, I can say something even stronger, right? I can say that if I have a proof that A equals B propositionally, then the same proof will work for A prime equals B propositionally, right? And how can I do this? Well, if I want to derive this thing, what I can do is, so you see if I write here, hopefully, okay, I want to derive that in context gamma, P is of type A prime equals B propositionally, okay? What I want to do is want to use element conversion for this type, okay? So element conversion says if I say that I have P of A equals B propositionally, and if I know that A equals B propositionally is judgmentally equal as type to A prime equals B, okay? Propositionally in gamma as a type. This is separate here. Okay? I just ran out of space. And then this is just the element conversion rule, right? But this here is just the congruence rule. And this congruence rule is this one, but it is for B and B prime to be the same guy. So I know that in context gamma, if A is equal to A prime, segmentally at A, and then if in gamma B is judgmentally equal to B, the same guy, at A, then I can use the congruence rule